Black holes could be holograms. In fact, the entire universe could be a hologram. At least, that's one part of the idea behind a recent study published in the journal PRX Quantum. The study is a deeper look at what's inside a black hole. It's also an attempt to better understand the idea of holographic duality. Holographic duality is a mathematical conjecture that attempts to connect theories of particles and their interactions and their theory of gravity. It's an interesting idea, even if it sounds a little out there. Using quantum computing to find out what's inside a black hole. Essentially, holographic duality posits that the theory of gravity and the theory of particles are equivalent, at least mathematically. Thus, what happens mathematically in the theory of gravity also happens in the theory of particles. For the most part, both of these theories describe different dimensions. However, gravity describes 3 dimensions, whereas particle theory consists of only 2 dimensions. The researchers hoped that probing this idea could help them understand what's inside a black hole. Enrico Rinaldi, a research scientist at the University of Michigan, focused on these 2 theories in the new study. In Einstein's general relativity theory, there are no particles, there's just space-time. And in the standard model of particle physics, there's no gravity, there's just particles, he says. Connecting the 2 different theories is a long-standing issue in physics, something people have been trying to do since the last century. By connecting these 2 theories and using quantum matrix models, Rinaldi and other members of the study were able to prove holographic duality. The idea was to combine what we know about particle theory and what we know about the theory of gravity. To start, they used simple matrix models made up of blocks of numbers. It's a standard framework used in quantum computers, where particle theory is represented by one-dimensional strings. These usually help researchers find the ground state, which Rinaldi says is important because it lets you create things from it. Using the models that they did, the researchers were able to describe what the gravity inside a black hole looks like. Is the universe really a hologram? Well, yes and no. When you think about a hologram, you'd probably think of holographic communicators from science fiction movies like Star Wars. In this case, though, what Rinaldi and his co-authors are referring to is the way the inside of a black hole meets with the outside. Because the inside of a black hole works off the theory of gravity. It is represented in 3D space as space-time moves through it. However, on the surface, the black hole looks 2-dimensional. This gives it a holographic look because we do not see it as a 3D object. This is because the theory of particles do not work in the 3 dimensions. As such, some believe that the rest of the universe may work similarly. However, there is no current proof to suggest that this is actually the case. Astronomers have unveiled the first image of the supermassive black hole at the center of our Milky Way galaxy. This result proves overwhelming evidence that the object is indeed a black hole and yields valuable clues about the workings of such giants, which are thought to reside at the center of most galaxies. The image was produced by a global research team called the Event Horizon Telescope, or EHT collaboration, and they've used observations from a worldwide network of radio telescopes. The result, a ring of fire surrounding the blackest of shadows, and is a powerful confirmation of Albert Einstein's theory of gravity or general relativity, which was used to predict black holes 80 years ago. It is also a feat for the team of more than 200 scientists who toiled for years to produce the image by combining signals from 8 separate radio observatories spanning the globe. It feels like looking at the gates of hell, says Heino Falky of Radboud University in Nijmegen, the Netherlands, one of the leaders of Event Horizon Telescope collaboration, which announced the result in a global set of coordinated press conferences. This is the end of space and time. Falke says the 2-year process of crunching the data and generating the image was the most emotionally difficult period of my life. The image is a long-anticipated look at the massive object that sits at the very center of our galaxy. Scientists had previously seen stars orbiting around something invisible, compact and very massive at the center of the Milky Way. This strongly suggested that this object, known as Sagittarius A, is a black hole, and today's image provides the first direct visual evidence of it. Although we cannot see the black hole itself because it is completely dark, glowing gas around it reveals a telltale signature, a dark central region called shadow, surrounded by a bright ring-like structure. The black hole is about 27,000 light-years away from Earth. It appears to us to have about the same size in the sky as a donut on the moon. The breakthrough follows the EHT collaboration's 2019 release of the first image of a black hole called M87, which is at the center of the more distant Messier 87 galaxy. This achievement was considerably more difficult than for M87, even though Sagittarius A is much closer to us. EHT scientist Chi-Kwan Chan from Stewart Observatory and Department of Astronomy and the Data Science Institute at the University of Arizona in the United States, and he explains the gas in the vicinity of the black holes move at the same speed, nearly as fast as light, around both Sagittarius A and M87. But where the gas takes days to weeks to orbit the larger M87, in the much smaller Sagittarius A, it completes an orbit in mere minutes. This means the brightness and pattern of the gas around Sagittarius A was changing rapidly as the EHT collaboration was observing it, a bit like trying to take a clear picture of a puppy quickly chasing its tail. The effort was made possible through the ingenuity of more than 300 researchers from 80 institutes around the world that together make up the EHT collaboration. In addition to developing complex tools to overcome the challenges of imaging Sagittarius A, the team worked rigorously for 5 years, using supercomputers to combine and analyze their data, all while compiling an unprecedented library of simulated black holes to compare with their observations. Scientists are particularly excited to finally have images of 2 black holes of very different sizes, which offers the opportunity to understand how they compare and contrast. They have also begun to use the data to test theories and models of how gas behaves around supermassive black holes. This process is not yet fully understood, but is thought to play a key role in shaping the formation and evolution of galaxies. Now we can study the differences between these 2 supermassive black holes to gain valuable new clues about how this important process works, said EHT scientist Keiichi Asada from the Institute of Astronomy and Astrophysics in Academia Sinica in Taipei. We have images for 2 black holes, one at the large end and one at the small end of supermassive black holes in the universe. So we can go a lot further in testing how gravity behaves in these extreme environments than ever before. Progress on the EHT continues. A major observation campaign in March 2022 included more telescopes than ever before. The ongoing expansion of the EHT network and significant technological upgrades will allow scientists to share even more impressive images, as well as movies of black holes in the near future. Although few doubted the existence of black holes, seeing them, or at least their shadow, was an immense challenge. Black holes have gravitational fields so strong that even light cannot escape. So they are defined by the shell of a black featureless sphere called an event horizon. But the holes can nevertheless be seen. As they consume matter that strays too close, they squeeze it into a superheated disk of glowing gas. Astronomers outside the EHT team will be eager for unexpected discoveries that could point to theoretical breakthroughs. When asked about the team's results, A.V. Loeb, director of the Black Hole Initiative at the Harvard University, says he is most surprised by the lack of surprises. A decade ago, he helped simulate M87, and he says his images look much like EHTs today. Even so, he says the team's result is an important milestone. An image is worth 1,000 words, and seeing is believing, he says. Now we've nailed the map of a black hole.